Good morning, everyone. My name is PJ Roberts. I'm a master's student with Rhodes University, and I'm excited this morning to be able to present to you on my project focused on estimating spotted hyena densities through camera trap bycatch data in Hluhluwe-iMfoloz Park. It's been a long journey that started in 2018, so I'm very grateful to be able to finally present to you. I just want to quickly run through my presentation overview. I will start by giving a background and rationale behind my project, giving a species status update for spotted hyena, then giving a regional context for my project, and then moving on to the methods and results, looking at call-ups and density estimates through this method, and then camera trapping and bycatch data for estimating density as well as space use and distribution, and then ultimately moving on to so what and what this means for the conservation and management of spotted hyena. Spotted hyena are regarded as the most common large carnivore in Africa, population estimates ranging from 27 to 47,000 individuals. Such a wide confidence interval of the population estimates, you can see that the population is generally very poorly monitored. In addition, the global population is in decline, and protected areas are becoming increasingly important for the long-term survival of the species. In a KZN context, there's been a recent increase in the popularity of trophy hunting for the species, which highlights the importance of further improved monitoring for the species across the province. In 2016, a conservation assessment as part of the Red List for mammals of South Africa, Swaziland and Lesotho was done, and in this report, the regional Red List status for spotted hyena was retained at near threatened, and this is conservation dependent. From the same conservation assessment from 2016, the three largest populations of spotted hyena across southern Africa were identified as Kruger National Park, without much surprise there, over 7,000 individuals, Kalahari Transfrontier Park at roughly 375 individuals, and thirdly, Hluhluwe-iMfoloz Park at roughly 300 individuals, based off of a 2010 report. The estimates of 300 individuals in Hluhluwe-iMfoloz Park is relatively consistent with historical work in the 1970s by Waitley and Brooks, who estimated the population to be roughly 36 to 46 hyena per 100 square kilometers, which translates to around 320 to 410 individuals throughout the park. Since 2003, there have been periodic call-ups to estimate hyena density. This was pioneered by Jan Graff for his masters in 2003 and 2004, and then adopted by park management in 2010, 2013, and 2015. Based off of these periodic call-up surveys since 2003, population has seen a dramatic decline between 2010 and 2013. This has raised levels of concern around what might be causing such decline and whether or not this in fact is a true representation of what has happened within the population. And this has prompted my research. The focus of my project was to re-estimate the density of spotted hyena within the park using an alternative methodology, namely camera trap data, and comparing this against the call-ups from 2013-2015 and facilitating a 2018 call-up to have a more complete data set there. I was also able to use camera trap data to better understand space use for the hyena population across the camera trap grid. As just mentioned, in 2018, I facilitated the call-ups consistent with the methods used in previous years by park management. We visited 27 sites over a period of 3 days, At each site, we sampled for 30 minutes, playing back recordings of hyena calling. And these calls are known to attract other hyenas, and we observed the number of individuals that came into the call-up. The response radius was set at 2.8 and response probability at 0.6, and these were values that were calculated by Jan Graff in experiments in 2003. Something worth noting now as I discuss the importance of calibrating response probability at a later stage. The results from the 2018 survey were relatively consistent with the 2015 density estimates of 12.07, 2018's was 11.41, and the 2013 estimates of 13.47. The camera trap survey that is run annually as part of the KZN leopard monitoring program consists of 46 sites with 2 cameras at each site, either on either side of a well-used path or road. The survey is run between March and June of each year, between 2013 and 2018. And I specifically used the hyena data images captured in these surveys and individually recognized each image in order to get individual capture histories. Using the spatially explicit capture-recapture framework, I was able to calculate density estimates. The question begs to be asked, does using a trap array designed for leopard work for spotted hyena? In order to answer this, I used the guidelines for trapping designs for the SECR by Tobler and Powell in 2013. The guidelines suggest that the trap array needs to cover a greater area than one home range of the target species. In the case of spotted hyena in Hluhluwe-iMfoloz Park and the camera trap grid, at least almost 10 home ranges fit within the camera trap grid. The length of the survey needs to ensure population closure, but without losing precision. This is acceptable at 45 days. And on average, we had plus minus 214 independent captures for each year, which suggests that the survey is effective at maximizing hyena captures. The distance between traps averaged 2.3 kilometers, which again meets the criteria of ensuring that multiple traps fit in within a home range of hyena. The SECR approach to estimating spotted hyena density has been done before a number of times since 2011. As you can see, estimates here are relatively low, between 0.85 through to 13.43. And the SECR approach is regarded to be robust, comparable, but also conservative. This makes my findings particularly interesting in that my camera trap density estimates were substantially greater than those from the call-up density estimates. Looking more closely at these results, we can see that the camera trap estimates on average were 16.72 hyena per 100 square kilometers between 2013 and 2018, whereas the call-ups estimates averaged 12.22 hyena per 100 square kilometers. And because the camera traps are generally conservative in their estimate, it would suggest that the call-ups are underrepresenting the population. Which brings me back to a point I raised earlier around the response probability and the need to ensure that these factors are regularly recalibrated and appropriate for the sample population. It's for this reason that we'll be rerunning experiments to better understand the current response probability of spotted hyena within the park. The camera trap data can also be effectively used to better understand space use and spatial distribution of spotted hyena. I was able to draw 100% minimum convex polygons for individuals who were captured at 4 or more sites between 2013 and 2018. A total of 62 individuals met this criteria, and I was able to confirm at least 19 females from the 62 individuals. Using these 19 females, I was able to identify core clan territories by taking individuals who overlapped by 66% or more and regarded them as being of the same clan. Using these stitched MCPs together, I was able to identify 7 groups across the 378 kilometer squared sampled area. Here's a representation of the 19 female minimum convex polygons across the surveyed area and stitched together the 7 clan territories identified. Looking closely at the clan territory size, average per Hluhluwe and average per Mfoloz, there was a high level of consistency with historical work in this regard. My estimates of 13.96 kilometers squared for Hluhluwe clans were consistent with work from Brooks and Waitley in the 1970s. It suggested the population of hyenas in this area had clan territories of 13 kilometers squared. And similarly, Mfoloz, my estimates had 34.61 kilometers squared, and Brooks and Waitley's were 39 kilometers squared. So what does this all mean? Well, I hope my presentation has showcased how existing leopard survey data can be used to produce reasonable density estimates and trends thereof for a species that is poorly monitored. We need to collaborate to better understand hyena populations in these key protected areas across KwaZulu-Natal, and simultaneously investigate genetic connectivity between these populations to understand whether or not the important corridors between protected areas are functioning for effective genetic dispersal for the species. And here is a list of my references. And I'd like to thank Rhodes University, the National Research Foundation, Izimvelo KZN Wildlife, Panthera, and Wildlife Act for making this project possible. Thank you.